Hello and welcome to our fifth in the series of customer webinars. The topic for today's webinar is transformer short circuit design. So robust short circuit design is key
about live talking.
external and internal.
Can you speak? This is a test. Yes. Hello.
Hello, and welcome to our fifth in the series of customer webinars. My name is Rajiv Kumar, and I'm the Director of Marketing for Virginia Transformer Corporation. The topic of the webinar is Transformer Short Circuit Design. This webinar will provide an overview of design and manufacturing considerations for providing a transformer designed to withstand short circuit. Presenting this webinar will be our Technical Director, Parminder Panesar, and the Research and Development Supervisor, Balakrishnan Mani.
Hello, and welcome to our fifth in the series of customer webinars. The topic for today's webinar is Transformer Short Circuit Design. So robust short circuit design is key to how transformer withstands external and internal short circuit conditions and how the transformer subsequently delivers its design service life. This webinar will provide an overview of the design and manufacturing considerations for providing a transformer that is designed to withstand the short circuit forces, the various failure modes due to short circuit, the design calculations for electrical and mechanical design to ensure short circuit performance, and the manufacturing considerations to build a transformer that meets the short circuit requirements. With me in this webinar is Parminder Panesar, who is our Technical Director, and Balakrishnan Mani, who is the Supervisor of our Research and Development Group. Parminder and Bala will be taking us through the content of the webinar. Thank you again for your participation. As many of you may know, Virginia Transformer is celebrating our 50th anniversary this year, and these webinars are being conducted as part of the 50th anniversary activities. And us reaching this significant milestone is primarily due to stakeholders and dedicated customers such as yourself. So thank you. Couple of notes on this webinar before we get into it. This webinar will be recorded and will be available for future viewing on our website and also on YouTube. Also, continuing education credits will be provided for this webinar. What you need to do is after the webinar, you need to just send a note to the marketing email ID that has been provided to you in the invite, and we will respond with the continuing education certificate. All question and answers as we go through this webinar should be put on the Q&A section of the GoToWebinar platform on which this webinar is being presented and you have logged into. We will collect those questions and we'll answer those questions at the end of the webinar. I would like to now invite Parminder Panesar, our Technical Director, to give an overview of the design considerations for short circuit design on a transformer.
Thank you, Rajiv. It's a pleasure to be part of this webinar to share our practices with the team here about short circuit, how we design, how we manufacture the transformers. So short circuit is a common fault conditions which is normally occur in electrical systems. So every piece of equipment, whether it's a transformer, motors, generators, they do get subjected to short circuits from time to time. And so all of these equipment, especially transformer, which we are speaking about, they're designed to withstand those stresses which happen due to short circuits. So short circuit are the severe fault conditions, which could be, three-phase faults, line to ground faults, or two lines to ground faults. So those are the condition which happens due to disturbances in the system and maybe some issues within the power system. So those are the conditions which transformer is always analyzed, and we look into the worst case scenario. For instance, delta wire, Y delta transformer, a three-phase fault will be more severe than line to ground, whereas a YY delta transformer where delta is tertiary, line to ground will be more severe condition. So Virginia Transformer goes through, the worst case scenario, it designs the transformer, analyze the strength it will have during short circuit, and so from there, all those information is passed on to manufacturing, and manufacturing has tight tolerances which our transformer is built to ensure the design aspects are maintained in the final product of transformer. I'm going to here invite Bala to get us started with the applicable standards for this particular short circuit strength of what we all watch. That's very basic point which we have to take care, and then from there we go into what extra we do as a corporation. Well,
thank you, Parminder. The standards which describe the requirement for the design to be complying to short circuit requirements are very few. The general standards which apply to transformers, say C571200, as inputs on X by R ratio, which actually determines the impact during the short circuit event. And then we have test standard, which covers the circuit connections and the passing criteria for the short circuit test when a transformer undergoes a short circuit test. And the next one is the design criteria is actually covered by an IEC standard. The IEC standard 60076 part 5, which has certain limits on various types of stresses which needs to be met during the design phase. And those criteria are based on the experience and the practices from other manufacturers. They are derived. And there are some inputs about the winding construction and how the winding and core construction impacts the short circuit design is given in C57125. And these are all the 4 standards, can be a quick reference for anyone who want to look more into the short circuit requirement. So what is actually a short circuit? So short circuit is a short between two line or two conductors which are at different potentials, which will tend to drive infinite amount of current, assuming the fault has 0 impedance. So at that moment, the fault occurs normally in the system. You have a circuit breaker that protects the system, and it protects all the equipments connected in the system. But there is a time lag between the fault and the fault circuit breaker operation. And during that moment, in any equipment which is connected will see a huge amount of current flows based on the rating and based on the design of winding and its damping effect. So those currents can be more or less than normal inrush current, but it depends, and it can vary from design to design. And coming to the force, when a short circuit current flows, the force exerted follows the Fleming's left-hand rule. So which is shown here. So your field will be orthogonal to the current, and the force generated will be an orthogonal to both component current and field. And since flux density, which is the field, dependent on the current, the force is actually related directly to square of the short circuit current. So the force can be very high, and the short circuit current normally ranges from say 12 times to 15 times the normal rated current, and it varies from system point of view and from design parameters. Now, how this will affect for various construction, Parminder will explain the construction and how it is affecting during the short circuit.
Thank you, Bala, for taking us through the standards which are applicable for short circuit and explaining brief about what short circuit how it happens, what it does to transformer. Now, going to the construction of core and coils, we would generally see the two common constructions, and the first one, as shown here in the picture on the top, which is rectangular core and rectangular coils on top of that. And so that this construction is more applicable for small transformers, generally rating of 2 MVA or smaller. And this is the preferred construction for those because this is an economical design. Also, in this particular type of construction, the windings, especially the LV, is a sheet winding, so which has a very minimum, almost zero axial forces, and the radial forces are still there, and those come between HV and LV. So under short circuit forces, it has a tendency to become a sort of circular in shape. So this is the reason it's not preferred for bigger transformer where short circuit forces are pretty heavy, and this is a weak design from that perspective, although it works for smaller distribution transformers. Now going to the circular core, which is a stepped circular core, and on top of that we have a circular coils. So now this is a very common construction for power transformers or medium power transformers. So a preferred construction specifically for a short circuit point of view, this is a very it has a good strength to short circuit forces because the circular coils and the LV coil which is inside, it is sitting very tight on the core, and core being almost solid mass built up of sheets, so that adds additional strength for those forces. And we're going to go through more details in about the winding construction in next slide. So the pictures here, they represent how the windings are manufactured. So winding actually is, we use a copper conductor, which is paper insulated for oil field transformers, or it could be aluminum for small rating of transformers, and depending on customer's choice also. So these are the four types of winding, and which will be utilized. And the sheet winding, which is generally used for a small transformer having high current, low voltage. So if it is a LV is 480 volts or 500 volts or less than 2 kV, this will be preferred construction depending on the current rating. And the benefit of this is it has a lower axial forces, but sheet does not have a whole lot of strength, mechanically for radial forces. So this is the limited use again. And then second would be a layer winding, and which is commonly used in industry as barrel winding. So here the conductor is wound actually from bottom to top or top to bottom, and putting multiple layers. And here again, the conductor is small, and it provides limited distance to the forces, or it has a limited inbuilt strength to the conductor. So now these two constructions are very common for a small rating transformer distribution size. Going to the other types of winding, which is helical, which is considering taking multiple transformers, multiple winding conductors together and winding in a helix form. And the last one you're talking about is disc winding. So these two windings are conductor is supported face to face, and separated by T spaces in between, which provide very good strength towards the axial forces and the radial forces in the transformer during short circuit. So so this is the preferred construction, helical and disc winding, and you would see this is a preferred construction for manufacturer, also a preferred construction from consumers. A lot of specifications which we get from customers, they do talk about a preference of helical and disc winding. And we do have, in these two windings are compressed within the transformer, and then once they're done during tanking stage, they are under compression force, which is equal to the short circuit forces. So that's the reason they provide a very good strength. From here, I think we'll go into the short circuit design and those aspects. I will have Bala explain those.
Yeah, thanks, Parminder. When a short circuit happens in a transformer, there is a huge rush of current flows in the winding. And this, during the current flow, we know there is a transformer action, which is the ampere turn balance, and the induction happens. And when there is an increased amount of ampere and ampere turn, there will be a force increase, and the force will be different at different location based on the design of the transformer. Say in this case, you see on the rightmost, we have a illustration which shows the winding, and then we have a tie plate or switch plate and clamps mentioned, and we have primary and secondary winding. So when a fault occurs, there will be a huge amount of current, and the current profile will have a combination of both AC plus some amount of DC component, which will be dampening out slowly based on the winding characteristics, which is mainly the X by R ratio. And when this happens, there will be a leakage flux setup, and the leakage flux will be bending, will be axial in the middle of the winding height, and it will be bending at the ends. So this normally can be divided into two components, X and Y, or R and Z components, to decide to use for our winding considerations, to select our conductor size and conductor thickness. And also one more important phenomena which will be determining the flux distribution will be an magnetic center between both coils, primary and secondary. And we shall see this in the upcoming slide.
Thanks, Bala. You talked about how it is or why it is important for the magnetic forces in the primary and secondary windings to be aligned. So what are some of the design considerations you want to incorporate to make that happen? Can you talk about that?
Yes. So when it comes to the winding construction, we have a design, and we will have winding height. Say, for example, LV is at 50 inch height, and HV is at, say, 49.75 or 49.875 height. So the point is, the magnetic center of the coils has to match in such a way that the design forces what we foresee at the design phase are actually the highest forces. So the manufacturing will have to make sure that the magnetic center matches within the certain tolerances of 1/8 of an inch, so that the forces actually considered in the design. And in an ideal condition, when the ampere turn is balanced and we have a magnetic center is matching, the short circuit forces, the axial short circuit forces, will be directed towards the magnetic center. But this is an ideal condition. But in reality, we will have the forces will be going to the top of any winding and or at the bottom, the axial forces, and those has to be controlled and kept in place by our clamping system design. So the clamping system is normally designed for the highest short circuit force, and if the short circuit forces are very high, in that case, the design has to be reviewed so that the clamping forces are higher than the actual short circuit force the transformer will see in its lifetime, so that the clamping system will protect in the event of an short circuit happens on the transformer. So the forces generated during the short circuit event is of two types. One will be a radial force, and then other one is the axial force. And radial force is generated by the axial flux density and the winding current interaction, and the axial force generated by the radial flux density and the winding current interaction. So with that, the constraining, the stopping point during that event is different for each forces. Say for example, radial force is resisted by the winding conductor for the outer winding, and the force is normally circumferential, which is a hoop stress or hoop force. For inner winding, it is a little more complex, and it depends on the construction. And conductors close to the center gap will see higher radial forces because you have more amount of axial leakage flux lines. When it comes to the axial force, it is resisted by the radial spacers and beam strength, and ultimately your clamping arrangement should clamp it together under any event of short circuit.
Thanks, Bala. So let's talk a little bit about what are the failure modes of short circuit and how do we design for it?
So the failure modes are different for radial and axial forces. And again, in radial force, it is different for the outer winding and the inner winding. For the outer winding, the force generated is of circumferential, and this resisted by the strength of the conductor, which is an yield strength of the conductor. If the stress is more than the yield strength, normally the failure occurs, and this is very rare for a transformer outer winding to fail during short circuit. And normally the improvement is done with the 0.2% proof strength of the material, and also work hardened material is ordered. And there is certain limits to not affect the manufacturing times for the work hardening. Parminder, you can talk about this work hardening and the 0.2% strength.
So it's very important point, just because when we design a transformer, so we design for lower eddies, and we reduce the conductor cross section of each strand within the winding. And when we do that, it weakens the strength to the short circuit. So it's a give and take. In order for us to do one thing better, we have to compromise the other thing. So what we do is, from there, we want to go for a thinner conductor, but it's work hardened, as it is the conductor is manufactured by our vendors, and we give proof strength of so many psi. They manufacture that, so we gain with the strength within the copper itself. In addition to that, another process to strengthen the inner winding is to use epoxy bonded conductor, which is a common thing for power transformers. So these are few things which we do to bring the balance between stray eddy losses versus getting strength for short circuit.
Thank you. Again, one more thing Parminder brought in, the eddy current losses. So when we have high evaluation rates and impedance is on lower side, we always go for the lower current density, which also adds additional strength for this short circuit event. For the inner winding, it is different, and it is classified as bending and a buckling phenomenon. And the forced bending, which is a failure which happens between the supports, the axial sticks. And what happens is when the stress is more than the elastic limit of the conductor, this type of failure occurs. And the figure on the right shows the failure. And the buckling phenomena is again divided into two parts. One is the free buckling, which is an unsupported buckling mode, which is mostly applicable for medium or large power transformers, and forced buckling when there is an inner support which is stronger than the conductor. So the buckling phenomena is of two types. One is free buckling and the forced buckling. For an inner winding, the stressors are the compressive load, and the first one we saw was the bending between supports, and the next one was the buckling phenomenon. In this first one, free buckling phenomena, this happens when we have a thinner conductor and higher conductor stiffness. And when this happens, you will see the failure is similar to the previous illustration. It can fail in a zigzag fashion. And for forced buckling, this happens when we have inner cylinder of higher thickness compared to the winding conductor strength. And this is normally applicable to smaller transformers in distribution range, where we have the inner cylinder is supported and it is thick. So we'll see here the failure mode due to axial force. So under the action of axial force, the winding conductors can bend between the radially placed insulation spacers. And this can damage the insulation on the winding conductor. So if the design is not able to withstand, when it is not able to withstand, then it can lead to a dielectric failure, even though the change in the geometry is not big. But if the insulation is damaged, it can lead to a dielectric failure. And next one is the tilting under the axial force. Tilting is mostly a common type of failure for large power transformers, and this failure can happen in a zigzag way. You see on the right, and this is again, we have some different configurations for failure for tilting. But when we go for CTC conductor with bonding, the strength increases quite a bit, because we have epoxy on the conductor which gets cured at 120 degrees Celsius, and which makes the conductor as one conductor for the short circuit condition. So coming to the short circuit force calculations and verifications at design phase of the transformer, and this is an important phase where we determine what are the short circuit forces and extreme short circuit forces for a given transformer and a given condition. This is normally done for the worst case scenario, say when we have a load tap changer LTC, or when we have just a DETC tappings. So this has to be done for extreme taps as well as the nominal taps. So in some cases, force can be high at positive taps, 16R. In some cases, it can be at 16L. And we at VTC, we use the Anderson program to do the short circuit force calculations. And this program is, as we know, this is a 2D finite element based program. So it gives certain results, and those results will be used to derive the force parameters to evaluate with respect to the standards. And again, the calculations will be different for different types of transformer. For example, if a transformer is just a delta Y transformer, DYN1 or DYN11, the three-phase short circuit is most severe. So the three-phase short circuit will be carried out. But whenever we have YY delta transformers, for those transformers, single line to ground fault is most severe. So we have to do both three-phase and single-phase short circuit force calculations. And these calculations can give us the extreme force, and this will be made sure that our clamping forces are higher than the worst case scenario short circuit. So that tells us that our design will withstand in the event of any fault. So after the short circuit calculations are done, the results has to be verified with respect to the standard and the limits. So in this slide, we shall see what are all the limits prescribed by the IEC 60076. For the hoop stress, also known as the tensile stress, the limits are, it has to be restricted to 90% of the proof 0.2% proof strength of the material. And for inner winding, it is different for CTC and regular strands. CTC, normally we use the bonded CTC, so you can go up to 60%. If it is non-bonded, then it has to be limited to 35%. And in some cases, some utilities can come and have additional safety margin on top of this. Say, for example, we normally see for a bonded CTC, it has to be limited to 55% of the 0.2% proof strength material. And so those will be designed, and if the when the stress goes up, so we have to change the design in such a way that the combination of conductor size and the ampere turn distribution to achieve this limit. And next, the forced buckling condition, it is limited to the 90%. In the same context, the other things are axial bending between radial spacers, which is again 90% limited, and beam bending is 90%, and tilting stress is 80%. And key spacer is normally has a limit of 8,700 psi. And these limits are for core type transformers, oil filled. If it is cell type, the limits are different, so which is not shown here, but we can refer to IEC standard.
Thanks, Bala. Now I invite Parminder to talk a little bit about the manufacturing considerations for designing transformers for short circuit.
Hey, Rajiv, thanks for bringing me back. See, Bala explained very well what are our consideration in design, what aspect help to improve the short circuit behavior of transformer. Now, we're going to go through manufacturing processes, and we heard a couple of terms very often in his presentation that, radial forces and axial forces. And so if these are two forces which are appearing under short circuit, what are we doing under manufacturing to make sure our transformer is robust and it will withstand those forces and will be back in service after a short circuit goes away. So we can talk a couple of things. Radial forces are the radial aspect of the forces is controlled by very good control with the like tight tolerances of the winding diameters. So it will include diameter of the winding itself in the radial build. So, the tolerances are very tight. And also when we land HV over LV and multiple coils, one over other, and the phase gets landed onto the core, tightness of those is very important. So, it's a manufacturing techniques which we use, and the tooling jigs which we use, which allow us a tight fit of one winding over the other and multiple windings over the core and ensure that, hey, they're aligned. The sticks, the radial sticks are there aligned, so they are making a good big line to withstand the forces. And so that's taken care radially. Actually, there is another thing. I'm going to go to the next slide to explain axial forces here. So on the axial forces, and when we started the presentation, we discussed some few advantages of using strip winding or sheet winding. Of course, that is not a common construction for power transformer, or not advised construction for power transformers. So here are a few pictures which show how the windings are actually clamped. So these key spacers columns, they need to be aligned perfect, and the alignment, we use sticks to ensure they are aligned properly, and also top and bottom blocking needs to be aligned. And these key spacers aligned, they align vertical within the coil, and from one coil to other coil radially needs to be in the same line. So these are a few things, and another thing which can improve the behavior of this clamping process is if we use isostatic presses, which actually keep constant pressure on the coil as it is being dried, and also another way which is less expensive way than isostatic is using spring loads. So these are requirements from some customers, and but most of things, it is not much known in industry. We could use a simple baking process and clamp the coils to the required pressure. Now this pressure which we talk, this actually is coming from what is the total compression needed on the coil, which actually goes back to the short circuit forces. So, and Bala mentioned in one of his slides that these forces at which the coil is clamped has to be more than the short circuit forces. And what this becomes very important, the drying process become important, because we do want to ensure the coil is getting to the right height within the tolerances. So if you have plus minus 3 millimeter tolerance or 1/8 of an inch, so it has to be maintained at the drying process. So we know, okay, the coil has reached to this point, and once the job is finally dried, vapor phase, and goes into tank, it will have the same tolerance. So by keeping tight tolerance on the height, we are ensuring they have the coils, HV, LV, regulation winding, all of them have a center point which is not shifted. So that will help actually to maintain the short circuit forces up to the design level. If they are unbalanced, those forces could be way more than actually design has calculated. So these are few things which are taken care in the winding process, and also the as we prepare the phase before we land onto the core. So when the phase assembly is completed, the coil is landed onto the core, and the connections are completed, and it goes into vapor phase drying or conventional drying process. So at that point, there are additional precautions which needs to be taken care before job is tanked. So drying process is very important to achieve 0.5% moisture in power transformers. And also at that time, we will measure the actual height of the coils in the clamp condition, ensure it's meeting to the required engineering value, and it's closer to what we did in the coil sizing process. Those things, they will ensure that the coils are magnetically, the magnetic center of the coil is the same. And exposure time is very important, because we have achieved 0.5% moisture in vapor phase drying, and whatever time the job is exposed when we service it before it goes into vacuum and goes through the before it goes to tank and goes to vacuum process. It has absorbed some moisture. So that is very important to control the exposure time. Journal guidelines is to keep it less than 24 hours and then maintain that. If it exceeds, there are some steps which has to take place to offset the high exposure time. Also important is securing the leads in place. So we use wooden cleats and nuts, fiberglass nuts, and the studs to secure these leads. It is equally important to secure them, because under short circuit forces, these coils will move, and the corresponding leads will also move. If one or other lead get detached from the cleats where it could end up in getting away from the supporting structure, and could reduce the clearance, and the job may not fail from short circuit forces, but it could have a damage from the electric failure. So those all things which add on to the precautions which we take as transformer is being manufactured. So throughout the process, starting from winding all the way up to tanking, there are various checks, and all of them are part of our process assurance. And these checks are checked by our technicians, our supervisors, and it depends on how critical it is. It has a higher level, and higher visibility of checking and ensuring that we have met the required tolerances, and the product is going to meet it's going to conform to the requirements. So overall, in the manufacturing cycle or the processing, so these are top bullet points. So the clamping pressure which is applied onto the winding before the job is tanked, and that is very critical, and it has to be more than, which engineering ensures the value given is more than the worst case scenario for short circuit, and manufacturing ensures it is measured as the pressure being applied to each coil or all three coils together. So and the supporting structure is important. How we are keeping that force on the coils there all the time, and they are locked in that position. So that is a very important, I would say, the most important thing, a part of manufacturing to ensure the job is going to be good for those short circuit forces. And then, depending on the type of design, engineering gives us, to limit the oscillation, they will give us the force which has to go onto the coils. So those are, and they also watch for if any of those vibrations are coming closer to the natural frequencies, and they will have those all taken care in the design itself. So, and also one more thing is, some of the power transformer would use insulated through bolts for the core yokes, and just to give added strength. So in the old conventional way, these bolts were of metal, and with the technology industry has acquired in the recent years, these bolts are only they're insulated fiberglass most of the time, and sometimes they are avoided, but adding these through bolts would make the job more it will make it better for the short circuits. So if there's a choice to use core bolts, and engineering would use that to give better short circuit strength.
Thanks, Parminder. So we talked about the design considerations for short circuit. We talked about the manufacturing considerations for short circuit. So what are some of the testing considerations when it comes to transformer short circuit testing?
Right, Rajiv. If you have designed and manufactured transformer, there should be a way to test it to ensure, hey, it has met all the requirements. And although the short circuit testing is not a common test, and it is very expensive. And one thing, let me go through the circuit diagram first before we get there. So the circuit diagram is the shorted one of the winding. We say primary and secondary. So we have to short one of the winding. Generally, the winding with a higher current is shorted, and so we have a lesser requirement of the current supply. And IEEE C571290, it provides all the requirement, which step it has to go into, what kind of connections, and how many cycles it has to go through for a short circuit. So just remember, at this time, we are supplying full voltage and full current under this connection. And our actually full voltage and the current will be very high. It will be actually based on the impedance. If it is 5% impedance, it will be 20 times the rated current. And so it's only for a few cycles, and then we have to check the behavior of transformer. And the passing criteria of this test is we measure impedance of transformer, which is per phase for each phase of the winding, and we measure same impedance after a short circuit. And the allowed variation is these are numbers for rectangular coils is 7.5%. For small distribution transformers, 2%, and for large transformers, it's 1%. So why we say impedance is because impedance is determined by the physical dimensions of the winding. So what is the diameter or the height? So any of the changes in diameter or height, which is a resultant of the forces. So that's the reason, if you measure impedance before and after, then it will tell you if there's much movement inside a transformer. So now coming to the testing, it requires very high power. So none of the transformer manufacturer has this facility, and it is done in special labs. That's the reason I said it's very expensive. So in US, we have a KEMA lab in Pennsylvania, and there's some other labs in the North America. But for bigger transformer, it has to go to Europe. But it doesn't need, every transformer does not need, in fact, it's not even one of the type tests. So it's advisable to use calculations to ensure, this transformer design for short circuit and manufacturing processes to ensure that it is going to be good for those forces. So, there's some transformer which are tested for, which are power transformer tested for short circuit, and every manufacturer has a list. BTC, we have the list maintained, and we have so many transformers which we tested in the past, and most of them are for for transit circuit 31 rectified duty transformers. And we take reference of the one which has passed, and our calculations, our concept is based on those, and then those extended to the other ratings. So this is the way industry has been using, and it is a destructive test. On top of that, it's not easy to get this test done. It needs a special testing facility, and those facilities generally have a long lead time, shipping and all. So again, short circuit testing is possible to do it. Needs to be very well done in advance, and there's could be special costing required for this test. So it's common practice for industry to ask for the calculations, verify the calculations, and control the process to ensure the transformer is good for the short circuit. So this is all which we are covering, and from here, Bala and we are ready for the questions. We would like to proceed from listen to those and answer them.
The first question is, on a power transformer, what are the loading guidelines? For example, on a 25 MVA, is 80% loading a good practice?
Thank you, Jana. So generally, in general, transformers are designed and tested at the full 100% rating of the nameplate. So if transformer is rated for top MVA of 14 MVA, top rating of 14 MVA, you can run it continuously on that load. Any unused rating, let's say you're at only 80% of its top capacity, it will just give additional life of transformer because it won't be running that hard, and installation life will increase. So yes, you can load a transformer at 100% of the top nameplate rating all the time, and then if you do use less, it will be just extending the life of it.
Can you comment if transformer noise could be affected by methods of clamping the windings for fault currents?
So transformer noise it comes from two aspects of it. The main noise comes from the core, which is magnetic circuit. It is made up of thin laminations. So the main contributor is the core, and the noise can be reduced by providing a better core material, reducing the flux density, and also providing dampening structure in between core and the tank. So a second factor to the noise is load. So transformer will have some noise, which is a major noise, will be from on a no load, and then on top of that there'll be some additional noise coming from the load. So those are designed, transformer is designed taking into account for what customer requirements are. As standard, NEMA TR1 are the levels which are given, and those are met for every transformer. Some customer has specific requirements of meeting a value below NEMA, and we have seen requirements of -10 decibels, -12 decibels below NEMA TR1, and those transformers need to be special designed and manufactured with all those practices into account. What is the second part of the question? The same one, you can repeat, please.
Can you comment if the transformer noise can be affected by methods of clamping the windings for fault
Okay,
currents?
so yes, the clamping of windings will make difference, and more than the normal transformer, the preventive auto, the reactive type low tap changers, which are Reinhausen most commonly used in the US, they have a preventive auto transformers, which are reactors, and they will contribute more noise if they are not properly clamped. So, but one thing is there, if the transformer coils are clamped to the required forces, a further increase of the forces will not reduce the sound. It will continue. So it under normal clamping forces, it will come to one sound, and it can't reduce it further. So for reducing the sound, there are various other ways, as I said, flux density and the clamping structure and the dampening structure between the current coil and the tank. So those are utilized.
Okay. If a transformer is subjected to a three-phase through fault and the fault is cleared before crossing the transformer damage curve, is there any need to inspect the transformer after the fault? A specific example is a fault in a downstream switchgear which is fed from a power transformer. Fault is cleared quickly, but the fault current is really high.
Okay. See, one benefit transformers have, in fact, any equipment, electrical equipment within transmission generation system, it is protected. So the main purpose of circuit breakers is to interrupt the fault current as before it becomes damaging for a transformer. If you have seen very high current, short circuit current through transformer, and depending on how many cycles it lasted, best would be to test the transformer for low voltage testing, which is very commonly done in the field, ratio, resistance, those tests. And the test which will be more promising is going to be the SFRA, so sweep frequency response analysis, which actually gives you, and which is known as a signature of a transformer. So once the transformer leaves the factory, if that test is done, and just remember that is not a standard IEEE test, it's a special test, and we have seen more and more requirement of that. So it has one signature, how the transformer is responding to various frequencies, and that signature should remain same throughout the life of transformer. And it does give you, it will indicate a variation if transformer has seen physical damages inside, if the coils have seen excessive forces and end up being D-shaping, or any other things have happened. So all those will be visible in SFRA. So you don't have to really take the transformer out and inspect it. That'll be the ultimate, requirement if you see a variation in testing as low voltage testing or SFRA asset.
Can winding temperatures affect the fault withstanding rating?
Winding temperature.
Winding temperature affects?
Can winding temperature
Short
affect
circuit
the
withstand
fault withstanding rating?
See, these faults are very short term. They last at the most a second or a couple of seconds, but it should be only a fraction of a second. So the thermal effect of these faults is very limited. So if transformers is running at 100% load, it has this, let's say, 65-degree rise temperature. It's running at that, and even addition of this very short-term excessive current will not add any severity to it. So although if transformer is cooler, it will be helpful, but it's not going to be it's not, it doesn't make a whole lot of difference either way.
All the questions.
So we appreciate the questions, and they were very informative actually. We're glad to share that. If you want to close it up.
Yeah, sure. Thank you, Parminder and Bala, and thank you all for your participation. We will continue the monthly customer webinars with various topics that will be of interest to the industry. Thanks again, and please, for continuing education credits, email your requirement to the marketing email ID that has been shared in the invite. Also, if you have any questions to follow up on this webinar, do email to the same address, and we will respond to you. Jenna, you had another?
I have 2 more questions.
Oh, you do have 2 more questions.
Okay.
Oh, sorry about that. Okay, go ahead.
Do unit auxiliary transformer in power plant require special considerations through SC fault compatibility?
Short circuit force.
Yes. Yeah. Normally, the unit auxiliary transformers requires additional verification, and based on the connection type also, it has to be verified from both sides of the fault. So that normally done in the design stage to meet all the requirement.
And final oil cooled job, if impedance value increase, how to reduce, sir, and what is the issue?
Please repeat the question.
Final oil cooled job of impedance value increased, how to reduce, sir, and what is the issue?
Final impedance.
Yeah, the question is not very clear, but
Let me read this. If impedance value, so for an oil-cooled transformer, if impedance value increases, how to reduce and what is the issue? So I don't understand what is. So I would request, I believe it's Charles Dominic. Could you retype your question, please? Are you saying how to reduce the short circuit?
see, one thing I can answer meanwhile as Dominic is retyping. So as the impedance increases, the short circuit currents will decrease. So short circuit currents are nothing but inverse of the impedance. So as I said, if there is 5% impedance, your short circuit current will be 20 times of the rated current. With 6, it will be 16.67 times of the rated current. So if the impedance is high, it will help you in short circuit and controlling the short circuit force, current, and the forces. On the other hand, it is not beneficial for regulation. So an impedance as per IEEE, it has tolerance for two winding transformers plus minus 7.5%. So manufacturer has that limits for the final tested number to be within that bandwidth. If customer is more particular about the impedance and the short circuit forces, they could ask for a smaller bandwidth, plus minus 5%, plus minus 3%. So just remember, anything which you ask for special beyond IEEE would need special either a special consideration in design and special consideration in manufacturing, and every manufacturer would consider the risks of it and will add up some associated cost if required, and then you have chances of either limiting your number of vendors from which the transformer can be purchased or adding some more cost to it. So there's a give and take, but that's a general rule. Impedance increases, short circuit will decrease, and in reverse is also is correct.
He did right there.
That's fine. So anyway, if anybody has any more questions, please feel free send an email to marketing email ID. We can respond back on those questions anytime.
Okay, thank you all very much, and we do expect a follow-up email as well from Virginia Transformer with any follow-up details you may need. And we'll see you again on the next webinar. Thank you all.
Thank you. Thanks.